Hello, my name is Andrew Grau, and this is my Physics 1 Lab 2. The purpose of this lab was to observe the trajectory of an object, compare it to predictive models, one of those models with only gravity and the other with gravity and air resistance. For this lab, I used Tracker, GlowScript, and Excel, and the principles at play here were Newton's second law and the kinematic equations. The main result, the gravity-only trajectory was greater, so higher and more range, than that of the actual trajectory, while the model with gravity and air resistance for me was slightly below that of the actual model. And I think this is due to error, as the graphs of the gravity and the air resistance should be very similar to the actual, and we'll get into why that error was caused later. So the main physics ideas and formulas, so we have the position update and the velocity update. Now those are obviously tied to Newton's second law, which states that an object's acceleration is directly proportional to the net force acting on it and inversely proportional to its mass. So that's what we've been talking about in class for the past couple of weeks, and that's a key principle in this lab. The experiment description. This is a photo of the tracker software where you can see also a frame of our video. We had to move our axes up because we threw it in the air, and I cut the frame to only fit that section where it was in the air because you couldn't actually see it hit the ground or the table. But that's fine. We just moved our axes up to where the ball started about 0.3 meters above that purple x-axis, and then it ended at 0, so at the x-axis. And then our system is just the white ball, and then the surroundings are everything else. And then you can also see we had a calibration stick that we had on a yardstick in real life and made a calibration stick in the tracker software. And assumptions for this, low friction, and we are not assuming no air resistance for one of the models, but on one of the other models, we are obviously assuming no air resistance. And then initial conditions, so the position at 0, 0.326, that's the height above the x-axis, and then our initial velocity, 3.138 meters per second and 2.2 meters per second. So the GlowScript program model, this was just taken off of the template on Canvas. So you can see our assumptions there. So the position and the starting velocity. The deltat was based off of our video frame rate. You can see our drag coefficient there. And then these are equations for force of drag, and then our net force, and then our position and velocity update formula. Then these are some photos from the simulation. These are only from the ones with drag, but you can see what was happening with the arrows, and then just the general trajectory of the ball. So explanation of assumptions, kind of how I found the velocity average of the x was just by taking the final position minus the initial and dividing it by the difference in time. So that's how we got that. And then there you can see the frame difference, or the difference in frame from the clip settings in Tracker. So conclusions/reasoning, as you can see, they are all very similar. The one with just gravity is a little bit higher than the actual shown in blue, and the gravity and air resistance is a little lower than the actual. That's unideal. I would prefer them to be a little bit closer, but going into our sources of error, the incorrect drag coefficient and the incorrect initial y velocity, I think were big components of why those were a little different. So for what if, terminal velocity happens when a freely falling object experiences zero net force. Our model in this specific lab does not predict terminal velocity. An experiment that you could do to predict terminal velocity of the object is just to have a great enough range and observe when the velocity of that object stops increasing, so when the acceleration is constant. So if I were to imagine an object being thrown straight up with the same initial speed as the experiment, would the time this object takes to reach the ground be the same, longer, or shorter than in the original experiment? So it would be longer because it has a greater y component to cover. And instead of doing calculations, I actually just ran the simulation again. And as you can see, to reach similar y final coordinates, I know they're off by a little bit, but they're very minuscule. You actually have to have a quite significant time difference. So that is how I know that it would take a longer amount of time if it were to be thrown straight up, just because it would have a higher y component, which is simulated here by the greater starting position as compared to the actual one. And that's my lab. Thank you.